record on this computer.
You got it?
Cool. Yeah, I think so.
Okay, cool.
Now let's share the screen again. Okay, cool. Let's see. Can everyone see my screen?
Yep.
Okay. Let's see. Just double check. Now, if I switch the screen, can you see that? Okay. Okay, so I'll go ahead and get started. Yeah, so my name is Dylan. I'll do a short intro about me in just a second. But my talk is just going to be about functional programming, React, and compilers with ReasonML. It's more focused as an introduction to Reason and some of these other concepts. But hopefully it will still be worthwhile for people. And yes, this is the Chicago ReasonML meetup, first virtual edition. Okay, so my name, and just to confirm, you guys, you see just like one screen. I'm in presenter mode, so I don't want to, like, there's some extra features. You just see the Dylan Irlbeck intern.
Correct. It's just the one.
Yes. Okay. So yeah. So my name is Dylan. I'm an intern at DraftBit. It's a startup based in Chicago that's building a no-code platform for React Native apps. Yeah, just like Webflow, but for mobile apps, we generate the code for you. I've been an intern there since January, and as an intern, I'm also a student at the University of Illinois in Urbana-Champaign, studying computer science. I'm in my third year. I've also interned at a few other Chicago tech companies. Relativity is a pretty big one, and then Zaptum is another startup. And I'm really interested in Reason and OCaml. Kind of got inspired by OCaml when I was taking, I'm not taking classes this semester, but when I did take our programming languages and compilers course, it was taught in OCaml, and that's kind of how I got exposed to the language. And I'm also interested in React. So a little bit of why I'm doing this talk. I love functional programming. I thought that I might be able to share some of my experiences and insights from the world of academia and teach people a little bit about a really nice paradigm that doesn't get as much attention as it should, in my opinion. I also love to teach people, and I think ReasonML has made me a better developer, and I kind of want to share that with all of you guys. I think I've built some really cool things, and it's kind of it's changed the way that I program in other languages too, which is kind of interesting insight, and I think it's important. So what I hope that everyone takes away, at least I hope you take away at least something from this talk. This is my first formal talk, so I'm hoping that it doesn't go too terribly, but I hope you take away an understanding of kind of the core concepts behind functional programming and how they're implemented in ReasonML, how the architects of Reason and OCaml use functional programming paradigms to make the language really, really effective. And then another thing I hope you take away is just ideas of what you might want to build in Reason. Through a bunch of code snippets and examples, I'm hoping that I can give you an idea of just how flexible the language is and how dynamic it can be in the sense that there's lots of different applications. So just hopefully I can inspire some people to start using Reason if you haven't already. So just a short slide. This is the logo for ReasonML that you'll see everywhere. But just so everyone's on the same page, so what is Reason? Why are we talking about it? Reason is a new syntax for OCaml that looks like and compiles to JavaScript. This was by design. The creator of Reason, Jordan Walke, wanted a language that was accessible to the most amount of people. And because of that, he chose to make it look a lot like JavaScript, but you still gain all the language features of OCaml because under the hood, it really is just OCaml. It's mostly functional, and it gets that from OCaml. We'll talk a little bit about what that means. But because it's mostly functional, again, you get a lot of nice properties. And because we use it on the front end here at DraftBit, it's just made our lives easier as developers using these paradigms. And you've also got 100% type coverage and a really powerful type inferencing system. Honestly, this is probably my favorite feature of Reason, is just the ability to not have to annotate your types while still getting 100% type coverage and soundness, and it just being really, really easy to refactor because of that. So let's first just dive into the functional approach to programming. And these are the three things that I wanted to focus on. There are many different characteristics of functional programming as a paradigm, but I chose these three. So the functional approach of programming, by the name, it's also the name for a book that I happened to keep on my desk until I was forced to work from home. And it talks about, it uses CAML. It's a language that came before OCaml for its examples, but it talks about kind of the concepts behind functional programming, much like I'm doing right here. But the first is that functions are first-class citizens. The second is pure functions, and the third is immutability. These are just the kind of core concepts of functional programming that I am gonna just quickly talk about in the context of Reason, but let's get into a little more depth. So the first thing is that functions are first-class citizens. The code kind of rendered a bit weird here with the comments, but what this essentially means is that functions are values too. They can be passed around just like integers or strings, and that allows you to do some really, really cool things. So here we're declaring an array of integers, and we're also declaring a double function that just takes in an integer and doubles it. And much like JavaScript, we can just use that, we can use the double function as a value when we pass it into this array.map function, and we can map it over the array, and we can return a new array. So we can pass around functions just like values. And you'll notice you can do this in JavaScript because there is actually a way to write JavaScript in a functional way, but this is just a property of functional programming, is that functions are first-class citizens. Another point about functions being first-class citizens is that you can do something called partial application, which is a really nice property. And you may not, this example might be a bit too contrived to really see the benefits, but it really shows itself when you're writing you have a really big code base. So in this example, we're taking an add function that it takes in two integers, x and y, and it adds them together. We then construct a new function, add 5, by fixing x with the value of 5 as the first argument. So now add 5 is a function, and it only needs to take in one parameter, which is y, and you can use it throughout the rest of your program. So then we can use the add 5 function to construct the values 11 and 12 by just passing in one argument instead of 2. So we can, using this concept of partial application, we don't need to set all of the arguments because we can manipulate functions in such a way, because there is such great support for functions in the language. And I just want to say that please stop me with questions at any time. I know that there are some things, some sort of niche cases in Reason where the syntax isn't super apparent, and I want to make sure that anyone can ask me questions at any time, because this should be more of a discussion about what the benefits of Reason are as a language. Okay. So the third thing is, the third concept of functional programming is immutability. And you hear this a lot, but it really has its roots in mathematics. Functional programming and computer science in general are really based on mathematics, and lambda calculus is a pretty abstract thing. But in mathematics, you should ask yourself, how are variables defined in mathematics? Only in computer science did we change the definition of variables to allow their values to be changed and their type to be changed. In math, when you declare a variable, it is just, it's really just a representation of a value. It's not supposed to change. And functional programming languages take advantage of this property. So in this example, we bind x to the value of 5, we execute the rest of our program, and if we inspect the value of x at the end of our program, we'll see that it's still 5. There's nowhere in the rest of our program the value of x could change. Because immutability, it basically just makes sure that once you declare a variable, once you bind variables together, both the type and the value cannot change. And again, this is very much rooted in mathematics. And I think I actually skipped over a slide. Yeah, okay, so this is the second point, was pure functions and side effects. So let's start with what is a side effect. This is the second property of functional programming. Side effects are just any sort of state change in a value other than, in values other than what's inside the function. So a side effect is just anything that manipulates global state. So like in JavaScript, you can, in React, really, you can manipulate the state object in the class-based system of React, but you can't do that in a purely functional programming language. So in this invalid reason example, this is the only code example where this is actually not valid reason. we try to increment the value of the variable value as it's passed in. This is not valid. We can't change that value. But what we can do in the second code example is just increment that value, and then we can return the value +1. So pure functions is a pure function is a function that does not have any side effects, and it also returns the same. By extension, it returns the same value for any input passed in. Like, so if you pass in 5, you'll always get the same value for the input of 5. And again, this comes back to math, where by definition, a input can only map to one output. In sort of the domain function space, you can only map to one output. And that's where functional programming gets this concept. So are there any questions so far before I go on to the second section? I'd love to get some validation. Is this making sense? Does anyone have any questions so far? I think something in the chat. What does sound mean? Are you talking about like type soundness, or like can you clarify, Alejandro? I'm a little bit confused about what you mean. Yeah. So type soundness, it's conflated a little bit with type coverage. They're very, very close. Type soundness just basically means that the types at runtime are the same as what they are at compile time. So you have you can have complete confidence in the fact that the types that you write in your code will be the types at runtime. So there's the types won't change during the execution of your program, except when FFI is involved. Yeah. So if you import like an OCaml, you can import a function from C and use it. Alan, correct me if I'm wrong. I've never actually used this property, but if you use a C function, you do lose some guarantees. And in the same way in Reason, you can just throw in raw JavaScript whenever you want to. That might also you might also lose the value of type soundness if you use FFIs, foreign function interfaces. Alan,
this allows you to circumvent things. So.
Okay. And your audio is working. That's good. But yeah, because Reason does compile the JavaScript, you can always throw in raw JavaScript as a last kind of last resort escape hatch. So thank you for that, Alan. Yes, these are all everything we just talked about are sort of like the theoretical properties of functional programming. But as I said earlier, Reason and OCaml are mostly functional. I believe Haskell is purely functional. I think I read that somewhere, but OCaml has some escape hatches by design. Does anyone else have any questions? If not, I'm gonna move on to the next section. Okay, cool. So the next section of my talk just talks about really compiler theory. I'm gonna take you guys through an example of just writing a small mini compiler in Reason, and I think this will show off a lot of the great features of the language. And this is where really I can add some value coming from the world of academic computer science. Okay, so why are we gonna write a compiler? In my opinion, it really shows off the core features of Reason. It shows off the type system. It shows off some of the properties we mentioned earlier about functional programming just in the Reason syntax. And honestly, at the end of the day, it's what Reason and OCaml is especially good at. So a few examples of software that's actually been built in at least in part by OCaml. Flow, if any of you guys have used Flow and Flow types in your JavaScript code, it's a static type checker for JavaScript. Again, Reason's type system just makes it really easy to represent programs and represent just structures. So Flow is written mostly in OCaml. This middle icon is for hack. It's another Facebook technology that really just threw types onto PHP. The hack compiler is written mostly in OCaml. And then finally infer, which is a static analyzer for Java, C++, C for mobile apps. All these are built by Facebook, and they all have the similarity as well that they're mostly OCaml. And again, that's because OCaml is just really, it's just really good at expressing types and relationships between your programs. So just to go over a little bit of what's in a compiler, and this is condensed. There are a lot of other steps that come in, a lot of optimizations that come into a real compiler, and some compilers also throw on a type system in the background. But for all intents and purposes, we're just going to focus on 3. So we have, first of all, we have our lexer, or our tokenizer. So from the input code of our program, we're going to create a list of tokens, which represents just the minimal set of characters in our program. I'll make this more concrete in just a second. The second step of our compiler is a parser, which turns the tokens from the previous section into an abstract syntax tree. It's just it's a representation of our program that is digestible by Reason and by other programming languages. And then the third step is code generation. So really, a compiler is just supposed to take one language and turn it into another. So we're going to generate our output code from that abstract syntax tree that we got from the parser. So, for example, JavaScript with the JIT just-in-time compiler, it compiles to bytecode, and I think there's some other languages that you can target with JavaScript, but a lot of these high-level languages eventually make their way down to assembly or bytecode, because you're really just a compiler is just taking one language and turning it into another and doing some intermediate steps as well. So we're going to start by, you have to define your front end and your back end of your compiler. So in this case, our front end, which is just the language that we write in, is mini C. It's what I'm calling it. It's a C-like syntax. It has only a few features of the language, but it's small and large enough to make my point. We have no type system, and our back end, which is the code we're going to be outputting, is JavaScript. So let's get into it. So we're first going to start by defining the tokens of our language. So for example, for an input program, this is what our C-like syntax, our mini C, looks like. Declares a function f that takes in no arguments and returns 1, the integer literal 1. So let's start by just defining what are the minimal sort of tokens that make up our programming language, our mini C language. So I want a little bit of interaction with the audience here. What could be our tokens? Does anyone have any ideas? And this is an example of a program. So how can we break this down into its smallest pieces of meaning? Does anyone have any ideas of what are our tokens?
So you got your declaration. I vaguely remember this, but that's all I got.
Okay.
Declarations and expressions, yeah.
No, you're on the right track, for sure. Does anyone else have any ideas of what the tokens are going to be for our language?
I'm just curious, do you mean that, like, by tokens, do you mean like what a lexer might output?
Yeah, I mean we're going to be building a lexer, so it's essentially what the lexer will output.
Something like def would be like a keyword, and f would be like a variable, and then you have like an open parenthesis and a close, and et cetera.
Right. No, yeah. So Alan's exactly right. So in our language, we have a few different tokens and a few different token types. So we have this def keyword, which will basically indicate we're approaching a function definition. We have f, which is it's really the identifier, is what it's called, of our function. So each function has a name, it has an identifier. So this is in this case it was f. We have our open parenthesis and close parenthesis to signal the beginning and ending of our arguments to our definition, to our function. And then we have integers, and then we have the keyword end. So we're just breaking down our program into the smallest pieces so that we can digest it into our parser and give it to our parser. Okay, so how do we represent these tokens? We're going to be using what's called a variant. So now we're getting into probably the most important feature of Reason, and the comments again shouldn't be highlighted. But we have this type token, and a variant allows you to express that a value is this or that. So it's instead of like this. So in JavaScript you have objects. They represent data, and you have like a book has a name and a price and a number of pages. But it doesn't, those languages don't really allow you to express this or that. So we have this token, and this token can be a def, it can be an ident, operand, and these are just, you can think of it as just like symbols or tags, I guess, but they have to be capitalized, and they're just a way of saying like, we're creating some sort of meaning from our program. So a token can either be one of these tags, and these will directly correspond to the tokens of our language. So this is what's called a variant. Okay, so how are we going to consume our input program? This is kind of a big question, so I'll just answer it. But we're going to be using regular expressions, and that's going to allow us to, when a stream of characters is incoming to our tokenizer, which is really just our program, we can say the first X characters are, we assign that to a def token, or the first Y characters, that's the identifier of our function. So regular expressions will allow us to match against the first X amount of characters of the input program and give that some meaning by assigning it to a token. Hope that makes sense. Okay, excuse this presentation lags a little bit for the code samples, but we'll get into it a little bit more. So let's start by defining our type. Here's another language construct of Reason. It's called a record. So a record looks a lot like a JavaScript object, and it basically just says you're going to give a name and a type to different properties of the type. So token type has a token, which is of type token from before. You don't need the annotation here. And then it also has a regular expression, which is a type of js.re.t. That's just basically just saying this is a regular expression. And this is what's called a record. It's just a different way to express a Reason type. Now we're going to be getting into how do we represent the combination of a token and a regular expression. So we have our def token, our end token. We have all these different tokens, and we're going to construct records for those. So for example, the def token, it has the regular expression, word boundary def, word boundary. It's that first token in the list. And that's going to just, we're creating some meaning out of both the token and the regular expression, which we're going to match, we're going to match later on to our program. But really, like, if you don't, it's not super important to have familiarity with regular expressions, but this is how we're going to consume our program. We're just going to match the first X characters to a regular expression, and that will allow us to say this is the def token, this is an end token, and we're just going to consume our program that way. Yeah, and please stop me if I have any questions. I know that I hope I'm not going too fast, but and if there's any questions on the language of Reason, language constructs, please ask me as well. Okay, so we throw it into a tokenizer function, and so we have our program. We have it, it just represents as a string, and then we have our tokens. We throw the program into our tokenizer, and then we log the result. So we're just passing in the program to our tokenizer, and then we're going to get a result. Pretty simple. Okay, so this is our output. So we have these values, which is saying this is what we matched on. This is the value. So we have def, we have the name of the function, parentheses, arguments, and whatever. And we also have these weird integers, which is just the JavaScript representation of those variants. Because when you're outputting a JavaScript or a Reason record and a variant, it represents that variant with an integer in the low level. And then we have the values of what we matched against. So in this case, that input program was def of x, comma y, comma z. So from before, and we have the x gets matched to an identifier token, the y gets matched to an identifier token, and so on. So this is the output, and as Alan was saying before, this is what our tokenizer is going to output. It's just a list of tokens that represent our program. Any questions at this point? It's very open-ended. I know that if you haven't seen a tokenizer before, it can be a little complex. So are there any questions at this point? Please speak up if there are any. Okay, I'll go ahead and move on. So that was our tokenizer. So now we're going to move on to the parser. the parser is going to take our tokens and convert it to an abstract syntax tree. And if you don't know what an AST is, abstract syntax tree, we'll get into that right now. It's basically just a representation of your program with nodes representing the meaningful parts. So for our abstract syntax tree, we start by defining our integer node. So how are we going to represent the integer literal 1? We need to find the minimum amount of information needed to represent an integer. So I'm going to ask again, does anyone have any ideas like what makes up an integer in our program? Like what is the minimum amount of information we need to store in our tree? Does anyone have any ideas? Okay. Well, it's essentially, you just need the value. It was kind of a trick question. There's no identifier associated with an integer literal. You just need the value. So this combination of this value is going to represent an integer node in our abstract syntax tree. Okay. So now we're going to get into a definition node. So how about the definition def, f, some arguments, some body of the function, and end. We need to see what the parts that we need to represent a definition node. So I'm going to let this slide kind of sit for a little bit. We need a name. That's going to be the identifier for our function. We need an array of arguments to the function, and we're going to have a body of the function, which is going to be an expression. That we haven't defined an expression node yet, but this combination of a name, arguments, and body is going to be what constitutes a def node, a definition node. Is this making sense to anybody? Because how you represent these nodes, this is ultimately what makes up our abstract syntax tree. So is everyone on the same page with this? Does this make sense? Okay, cool. So now let's get into some more reason code. Again, excuse the lag. So this might be a little bit overwhelming, but we're just gonna define what we just saw with defining the nodes in just raw markdown. We're gonna turn that into reason. So we have our internal AST nodes, which is, so our integer node, it has a value. As you can see up top, this is just another record. And then we have all these other types for different nodes. We have a call node, which is just calling a function g, maybe call like add of xy. We have a var ref node, which is just a variable. And to represent a variable, all you need is an identifier. You need a string. And then you have this expression node, which can be a call node, an integer node, or a var ref node, which is, again, just a variable reference. And as we saw in the last slide, we have a def node, which is the combination of a name, which is just a string, a bunch of arg names, which is an array of strings, and then we have a body, which is, again, just an expression. So it's just turning what we saw before with this representation. We have a name, args, and body. We're going to convert that into a reason type. Okay. And these are our top level AST nodes, which is just our def node and our expression node. Okay. And yeah, please stop me with any questions. This, like, you kind of have to understand all of this in order to really see the value across the compiler. Okay, so let's remember that we want to turn this input program, this input C-like program, def f of x, one end, into an AST, an abstract syntax tree. And that abstract syntax tree is going to have a def at the top level. It's going to have a name, arguments, and a body. And the body is just going to be an expression node as well. So that's just the conversion that we want. So now we actually need to parse the tokens that we got from the tokenizer. So what is that going to look like? So how do we parse integers? So our integer is, we're gonna take in a list of tokens, and what we're gonna say is if an integer variant is at the front of the token list, we're going to consume that, and we're gonna construct an integer token. We're gonna get an integer token and the new tokens out of it. So this line is saying The consume function returns a tuple. It returns 2 values, and we're just going to destructure that into the integer token and the new tokens. We're then going to say, once we have the integer token, we're going to construct an integer node by casting the string into an int. And then we're going to construct an expression node that wraps that integer node. So this expression node is just going to represent an integer inside our program, and we're gonna give the new tokens back to the caller. Okay. So, sorry, how do we parse expressions? So again, an expression can either be an integer or a call. The expression is the body of that function that we talked about earlier. So it was, in this case, it was the integer literal 1, but it can also be a call, and a call is just a function call. So that because there are 2 options, we need to kind of look ahead in our token list and see what the next tokens are going to be. So essentially, we peek at the tokens in the list, at the first token. If we peek at the first token and it's an integer, we're going to parse an integer. Otherwise, we know that we're going to have to parse a function call. So really, there's 2 options for what an expression can be. It can be an integer, or it can be a call, a function call. And then we just pass along the tokens throughout this program, creating that nice control flow. Okay, so we're going to put it all together, and we're going to construct our abstract syntax tree. So from a list of tokens, we're going to turn it into a bunch of expression nodes, def nodes, integer nodes, and so on. Okay, so we have our parser. Our parser has this internal recursive parse function. That rec keyword at the front of the function just lets the compiler know this is going to be a recursive function that can call itself. So the parse function takes in the list of tokens, and now we're going to see an example of a switch statement. So it's if you come from JavaScript or some other languages have a switch statement, it's just a nice way of providing cases that you can match against. But the reason switch statement is a bit more powerful, we'll see that when we match against variant types, but it's just a nice, easy way, and it's a very readable way of saying if a variable has this value, you do this, otherwise you do this. So in this case, we take in our tokens, and we're going to switch on the length of the incoming token array. If it's 0, then we're going to return an empty array, and that empty array is our abstract syntax tree. If there's no tokens, there's no abstract syntax tree. But for every other value of the length of the token list, we're going to start parsing. And because the definition is the top level of our program, we know that we're going to parse the definition for if we see any tokens incoming. So what we do is we call parse def with our token list. We get back the parsed definition and the remaining tokens, and then we recursively call the parse function on the remaining tokens of our token list. And we do that, and by the end of it, we'll have a bunch of definitions because, again, definitions are the top level of any of our programs in this mini C syntax. Okay, I'm going to pause here just for a second because this one code snippet actually shows off a lot of features of Reason. Is there anything about this that is tripping people up? Do people understand what I'm even trying to do here? And some not just questions, but some yes or no's would be helpful too, because I don't see anybody, so it's hard to know. Okay.
Makes sense to me, Dylan. You're doing great.
Okay, cool. Yeah, so then this snippet got a little messed up, but well, I got one more thing in the chat from people. Yes, okay, that's great. Okay, so for an input, this is messed up, but for an input of def f of x of 1, that should be a 1, and we get this abstract syntax tree. So it's a def node with a name, arg names, a body, which is an expression node, which wraps an integer node, which has a value. So we've constructed our abstract syntax tree. It's just it's a tree that is made up of def nodes, expression nodes, integer nodes, and so on. And it's highly recursive. Okay, I just paused for questions, so I'll keep going, but yeah, please stop me at any time. So now we're going to generate some JavaScript from our input abstract syntax tree. So again, the whole point of a compiler is taking in an input program and giving out some output in another programming language. In this case, it's JavaScript. So we have our abstract syntax tree from before, and we need to turn that abstract syntax tree into valid JavaScript. So as you can see in the screenshot from below, we have our def node, and we need to turn that into a function f of x and returns 1. We need to have all valid JavaScript syntax. So again, this is the code generator portion of our compiler. And again, our generate function will be highly recursive, just like the parser. It will call itself in some kind of weird ways because the expressions are made up of calls, which might have expressions as the arguments. So it's just, there's a lot of recursion going on here, just like any other program. Okay, so how are we going to generate code for an expression? So we know that the incoming type, the type coming in is an expression node. So we're going to switch on the expression node. If the node we're looking at is a call node, we're going to do a few things. We're going to take out the name from that call node. That's the name of the function being called. And then we're going to parse out the, we're going to grab the argument expressions. And we're going to join those together to form a string. And then this is the reason syntax for interpolation with strings. So we have the name variable, and we put it inside a string, and then we're going to return that string. And notice, you probably guys have noticed, there's no return statements in all of OCaml, and that's actually, I think that's a feature of most functional programming languages, is because I think a lot of the early academicians just saw a return statement as a waste of space. It really doesn't do anything because at the end of any function call, at the end of any program, you're returning an expression by default. So there's no need for a return statement. It's just the last expression in any of these switch statements is what gets returned by the function. So again, if it's a call node, we take out the relevant data and we return a string because we're generating code at the end of the day. If, however, our expression is an integer or a variable reference, we don't really have to recurse at all because we've reached the most basic level, the most basic part of our program. So if we've reached an integer node, and I kind of skipped over it, but you can see that the integer node was a variant. And we can, because the integer node is made up of a record, that's kind of the data associated with the type, we can pull out, with this switch statement, we can pull out that record. I can't really think of a good analogy here, but as you can see, like we have the integer node, we have the parentheses, and then we have the lowercase integer node. That just gives us access to what's inside the integer node variant. And I realize now the names make it hard to distinguish, but this pattern matching and this pulling out of data in this nice way makes a lot of sense once you write more reason. And I can answer more questions if needed. But if it's an integer node, we pull out the integer and convert it to a string because our output program is just going to be a string anyway. If it's a variable reference, we don't have to do anything. It's already an identifier, so we just can return it. Okay, again, sorry for the lag. So we have now our main generator function. This is the top level function that we're going to call to construct our JavaScript code from our input abstract syntax tree. And in normal tree fashion, the top of this abstract syntax tree is just going to be a root node. So we take in the root node and we switch on the type of that node. If the top level root node is an expression, then we generate an expression. Kind of says it in the code, but we can pull out the expression node and generate an expression from that expression node. Otherwise, if it's a function definition, then we can enter this other switch case. In doing so, we kind of pull out some information from the def node, we join the argument names together, and then we recursively generate the body of that definition. Because again, the body of a function definition is another expression. So we'll recursively call our generate function, and then it'll match into the expression node, and then it'll generate an expression. And again, you're seeing like you can already see the JavaScript parts. You have the function, which is hard-coded. You have the name of the function definition, which we're passing in via interpolation. We have all the arg names, and then we have our JavaScript return. I see someone talking in the chat. Got distracted for a second. The parser is coded by hand, right? No generator. Parser is coded by hand, right? No generator. The parser, yeah, so correct me if I'm wrong, Cristiano, but the parser, so OCaml has some tools built around it for generating parsers. I did not do that. I wrote this parser in Reason by hand. Does that answer your question? Okay, cool. Yeah, at the University of Illinois, we used parser generators. You give it your programming language, you give it some regular expressions, and then it gives you back a parser. So you don't even need to write the parser yourself. But in this case, I chose to write the parser with Reason, as you saw in the previous section. Okay, so let's put it all together with the compiler. So now we're just going to, we have our compiler.re file. We take our input program and we pipe it into the tokenizer using this pipe first operator, which basically just says take program and put it as the first argument of that make function. And that will return a list of tokens, which we pass into the parser. And the parser will return, our abstract syntax tree that we pass in to the generator. And then what we get from the generator is what we're going to return from the compile function. And then we can just call our compile function from above with our input program. And that's our compiler. So if we call compile with a definition, you see the JavaScript being represented. And what's neat is that our mini compiler also supports arbitrary nested expressions. So as you can see here, inside the body of the f function, we have a function call, but the arguments to that function call are themselves expressions. And because of the way we set up our parser, everything will get parsed correctly because we're recursively calling, when we get to the body of the function, we enter a call node, and the call node has a list of arguments which are expressions. So then we call the expression parser function, and it just, again, it's highly recursive, but we can support any amount of arbitrarily nested expressions. And then you can see the JavaScript that gets generated below. Okay, so to do a quick recap, because we touched on a lot of different things in that section. So the structure of a compiler, and this is a pretty bad image that I pulled off from the web. We have our tokenizer into our parser, which goes into our code generator. And as you can see in this image, the third step is actually a type checker. In OCaml, that exists. Our mini C language does not have a type system, so we omit that part. But in a lot of programming language, in a lot of statically typed programming languages, you do the type checking as part of the compiler after you generate the abstract syntax tree. And that allows us, because we can say, if we have a plus function, we expect that we're going to have 2 integer nodes on either side of the plus function. And if we don't get 2 integer nodes, then we get a type error. And we can say exactly where that type error is. And again, it really improves the developer experience because we have that type checking. So again, or adding on to the knowledge we hopefully learned about a compiler and what makes up a basic compiler, we also saw a lot of examples of the features of Reason as a language. Notably, we saw variance and pattern matching, which is saying that, did someone try to talk right there? Okay. We have type something. It can be this or that. Variants allow us to really express a large variety of use cases because it's very flexible. And the pattern matching, as you saw with the switch statements, is just really, really gorgeous and easy to refactor and stuff. We also saw records, which kind of look like JavaScript objects, which is just when you need a more advanced way to represent your data, you can use a record instead of a variant. And then we saw type inferencing, which is arguably, again, the most powerful feature of Reason in OCaml is not needing to annotate your types everywhere by saying, oh, our tokens is an array of token types. We get that for free because the OCaml compiler knows it can just infer what that type is based on the structure of our program. And then finally, so type inferencing. We saw the Reason OCaml type system in action. So this is just a screenshot from my terminal. I hovered over the compile function, and if you, depending on the language server that you use, you can see clearly what the input and output of the compile function is. It takes in a string and it outputs a string, and it does that just by default out of the box. You can hover over any function, any value, and because your programs are 100% type safe, the type inferencing engine will give you back what the type of that value, or that variable or function is supposed to be. So in the compile function, it already knows that it takes in a string, gives a string. I don't have to do any annotations there. The error messages are also insanely great. I can't, like, when you have a large enough code base, this makes a lot more sense, but the OCaml compiler really is super clear about where and what mistakes you're making. So in this case, I tried to call the compile function with a argument of 1. It tells you exactly this has type int, but somewhere wanted string, and it even gives you a recommendation of how you can achieve the argument type that you want with the string of int function, which just converts an int to a string. So really nice compiler. I've also failed to mention that OCaml is insanely fast through all of this. That is just the nature of OCaml is that and why in some ways Reason is a lot better alternative than TypeScript is just because when you have a large code base, the compile times are just insane. Okay, so the last part of my talk, I want to kind of bring it back to, I guess, reality, because most people aren't going to be writing compilers in their free time or for their full-time jobs. I haven't quite decided if I want to get a PhD yet, but I mean, I love compilers, but most people, you won't end up ever needing that knowledge. That was just to show off a lot of features of the language. So now we're going to talk about really what makes, why Reason is kind of the future of front-end web development. And I think it's arguably one of the most important takeaways of this talk is having something tangible that you can take into the real world and use Reason with. So we're going to get into Reason React. So we've talked about Reason as a language. So now what can we do with it? And what presents itself as Reason React. Again, Jordan Walke, the creator of React, was also happened to be the person who created Reason. So there's a lot of overlapping concepts. At DraftBit, we write our React code with Reason to get some of the benefits. And because because Reason compiles to JavaScript, it's nice. It's really easy to integrate into an existing JavaScript code base. And there's a lot of tools around that process in the Reason community. So writing Reason, because it compiles to JavaScript, it's a natural way to write React. And again, what are the core concepts of React? If we can dumb React down to the most basic level, what are the things that are important? The first is to minimize application state. We really saw this with React hooks. It provides a really nice API to only change state when you want to, and in the least amount of with the least amount of time as possible. And again, in Reason and functional programming, a goal is to have immutable state and really just minimize the amount of state that you're carrying. So React and Reason share kind of that property. And minimize side effects. Again, with hooks, there's not many options. There's not as much options to change the state of your program. I mean, before React, I wasn't writing code before React, but I've heard that there was a lot of just you look at the DOM, you say what node you want to change, and everybody is kind of going at it, and there wasn't a lot of structure to how those side effects were being managed. So again, because Reason is mostly functional, you're allowed to do side effects. You're allowed to write React with Reason, but you also have those side effects be minimized by using Reason and by using React. So let's just go through a few examples of what Reason looks like. So this is just our intro example, which is, you'll notice that it looks a lot like JavaScript. JSX comes with Reason React. It comes built in. just with a few quirks that you need to keep in mind. So we have our arguments, and this is an example of a named argument. If you use this little tilde, when you call the function, you have to say like name equals a string hello. And you can reorder, if you have named arguments, you can reorder the arguments in any order you want. So if I had name and value as props, I could just say value equals 5, name equals hello, and I could use whatever order I want when I call this function, call this React component. We see React hooks, and if you haven't seen React, then I apologize. I'm making a lot of assumptions here, but React hooks are another built-in thing for Reason React. And then you have JSX, and the only one of the quirky things is that you have explicitly typed elements. So we have this react.string function that explicitly says we are creating a string, and we're going to throw that string into the DOM, into the JSX. JavaScript, you can kind of just loosely throw variables in, but you have to explicitly type them in Reason React. And then you just have this decorator at the top that just says you're writing JSX in React, and it's required, but you get used to writing it. So what are the main practical benefits of Reason React? We have types, which makes refactoring extremely easy. We have those explicit handling of elements with React.string, which some people think is, it's mixed opinions on whether or not that's a good thing, but I like types, and seeing that explicitly React.string, I know that someone is inserting a string into the JSX. And then we have first-class language tools like immutability and switch statements, which we'll see make writing React really, really easy. And so 2 more examples, and then that'll be the end of my talk. So one example is routing. So Reason React comes with a built-in router, and the combination of React and Reason plus a switch statement makes case handling in with your routing extremely easy. So we have this Reason React router, and we're basically just getting the URL, which is hello.com/book/10, and then we switch on that URL path, and we just say if it's book, ID, and edit, we can pull out the ID variable, which in this case is 10, and we can use that and return and just return whatever we want to. But it makes it really easy to see what the different cases are for a URL. And if anything is not handled by your switch statement, the compiler will also yell at you. So you'll know to handle every single case in these switch statements. So routing I think it makes it really clear and illustrates the beauties of a switch statement. But Reason React comes with a router built in, and it's like 20 lines of code. So the API is really small too. Okay, so the last example is Apollo. So if you use GraphQL, if you use React, you'll likely be using Apollo for your client and/or your server. So in this case, we're going to see why writing Apollo in Reason with Reason is stupid simple too. So we have our GraphQL query just gets, and this is fully typed by the way because of how OCaml works. So if you in this current user object, if you throw in a property that's not actually in your GraphQL schema, you'll get a warning, or actually you'll get a compile time error saying that your GraphQL query is not typed correctly. So before you even execute the code, you'll have confidence that your GraphQL queries are also typed correctly. And then down here we see our React component, and we can see after we call use query, we know the states of the query. If it's loading, we can render a paragraph or a p tag with loading. If we get data back, then we can render something else. If we have no data or if we have an error, we can just render whatever we want as well. But the combination of Apollo, Reason, the switch statement, it makes it just really easy to express what states you want to render in your application based on the value of the query. If it's loading, if it's returning some data, etc. I think it's elegant, but even if you don't, whatever. I think it is. So what did we hopefully learn from this talk? I'm hoping you learned something. But the first was functional programming concepts. So like we talked about, we have immutability. We have this notion of pure functions and how pure functions don't allow side effects. And then we have functions as first-class citizens. You can pass functions around. You can use partial application to construct some really, really elegant programs. We took a deep dive into the language and some of its features by writing a mini compiler. And again, OCaml is used in a lot of real-world compilers. So I thought this was a nice way to kind of give a taste of what's out there, but also be a little bit manageable to understand. And then finally, we saw a few examples of how to use Reason React to build really powerful and extensible web apps. So writing Reason at DraftBit for our front end has made it really nice and easy to refactor, and especially as an intern getting started, I was able to make some good contributions early on, in my opinion, because it was really easy to extend Reason apps with confidence that stuff won't break, because once it compiles, it usually works, surprisingly. Okay, so I just want to say thank you for everyone listening. That was my first talk as an intern. It was scary learning Reason. It was scary making this presentation, but I appreciate everyone listening. And if you have any questions, I'm definitely open for them.
Thanks for the talk, Dylan. One of the questions that I had is how would you say that the tooling is for OCaml around compiler like type systems in general? Like, are there a lot of existing libraries for things like doing type checking in like a sort of established styles? Or is most of the architecture that's out there kind of very specialized to specific languages? Because you mentioned that there are compiler like parser generators, for example. Yeah. And I'm wondering if, like, since OCaml is used for other types of compilers, maybe there's similar things for type systems.
Yeah. So so what I mentioned earlier was there's a few tools in OCaml for creating parsers, and there's some software out there for just defining the tokens of your language and then defining kind of the semantics. There's code, there's software out there to generate parsers. That's what I used at school. In terms of other tooling around the type system, I don't think I've spent enough time in the OCaml open source community, but I know for a fact that it's really easy to generate parsers using some stuff for OCaml. Yeah.
Thanks.
Does anyone else have any other questions or feedback?
Yeah, if I may.
Yeah.
So I heard somewhere that languages like TypeScript or Java, they are best effort type system, and ML family languages sound type system. So somehow it's like better or more robust. So
yeah,
how does it different, and like when does the best effort type system fail to check the type in the compile time?
Yeah. Okay, so I'll try and answer that in a few ways. So the first, Reason versus TypeScript has been a pretty big debate. Peter, who's in this Zoom call, gave a talk on Reason versus TypeScript and what the trade-offs are. I would say that TypeScript it tries to throw types onto JavaScript. It doesn't start with a type system and then build the syntax and the language on top of it. So you get some weird. I haven't written a lot of TypeScript, honestly, but you do get some weird edge cases where TypeScript treats like the number one is like there's just some weird edge cases with TypeScript that you don't get with Reason. In addition, the error messages in the TypeScript compiler I think can sometimes be really intimidating, whereas the Reason error messages when you have incorrect types are super straightforward and tell you exactly where you made a mistake and even give you recommendations on what to fix. Java, you have to annotate all your types, whereas Reason, everything is inferred. So I don't know if Java has added any sort of like auto or way to not, it has added type inference, but a lot of those languages, I mean, the Hindley-Milner type system is what really makes up the ML family of languages. And that had research go into it. I mean, OCaml's been around for 20 years, but the Hindley-Milner type system has been around for like 50. So it's gotten a lot of research, and languages based on it, like Elm or OCaml, are just extremely powerful and just have arguably probably the best type system. I don't really know of a lot of other type systems, but TypeScript and Java just don't come close to Reason in terms of their type system.
Okay, thanks.
Yeah. Anyone else have any other questions? Okay, well, I mean, seeing as this is a meetup, if anyone wants to, screen share anything or talk about anything in particular, we still have some time. It wasn't just supposed to be a talk, but thank you again for coming, everyone, and I hope you learned something.
Thanks a lot, Dylan. That was super beneficial.
Appreciate it, Peter. Thank you. And this was recorded, so I hope if anyone wants to watch it later. And thank you for everyone in the chat. I appreciate the validation.
Yeah, I agree. I thought it was pretty interesting. I didn't really know much about compilers, so I think it's a very concise and a good rundown for somebody who doesn't have that knowledge.
Yeah, thanks, Chris. Yeah, a lot of the stuff you really only get exposed to in academia, for better or for worse. So hopefully I was able to give some insight there. If anyone wants to show off a project you're working on in Reason, then by all means go ahead, or if you have something cool you want to talk about. Otherwise we can sign off. And if you're interested in building mobile apps with React Native, but not writing any code, please go check out DraftBit. I think it's a really cool company. I'm biased, but we're getting the platform more stable and effective every single day. So
I hear you got a new filter menu too. That looks pretty sick. Or component menu.
I was gonna say, yeah, the component menu. I mean, there's a lot of new things. I don't know, when was the last time you played around with DraftBit?
Oh, maybe 2 weeks ago.
Okay.
Oh,
Okay.
My internet. But yeah.
Yeah, no worries. Yeah, we're adding new things every day. I mean, the component menu and a lot of our just general UI interface is constantly changing and I think getting better. So the component menu, I think, was part of that refactor. So much is changing that like I honestly can't recall what it was like even 2 weeks ago. But yeah, it's getting better every day. All right, well, everyone stay safe and healthy. I think if no one else wants to talk about anything, then we'll probably see you next month. I don't know if you have a speaker, but.
All right, thank you.
Yeah, thanks everyone for coming.
It seems like there's a question in the chat.
Is there? Was there a specific reason to use array type as opposed to list type? Okay, yeah, so OCaml and Reason have two different types of data structures for lists of objects. So the first is the built-in list type. The second is the array. So I used array because that's what's pretty familiar to me. So array, the array is mutable. Mutable in the sense that you can change what's inside, and that's why, as another example of why Reason is purely functional or mostly functional. It also gives you index access. So just when I was implementing the peek function, for example, if I wanted to peek X tokens ahead, then doing that with a array made it a lot easier. A list is just a linked list, so you would I don't think you could access it with an index. So I just chose array because that made sense to me. But I think if you're an OCaml enthusiast, you'll probably use the list more often.
Yeah. I can expand on that a little bit.
Yeah,
because I have some experience with JavaScript and linked lists and versus arrays. So and some of this you might have mentioned, but lists in Reason are linked lists, so they have linear time access. Like you want to go to the nth element, you have to do n operations to get there. or order n operations, whereas arrays are basically like JavaScript arrays, or like a lot of array languages which support arrays, where you can just say, constant time, go to the nth element. But lists have constant time concat, or I shouldn't say concat, I should say prepend, where if you want to put something on the front of a list, then it's a very fast operation. Whereas with arrays, if you want to say prepend something to the beginning of an array, you have to copy all of the remaining elements of the array. There's various other more sophisticated data structures, which obviously have different characteristics around that. One of the cool things about reason arrays specifically is the way that the compiler compiles them. It also does a similar trick with options, where it uses null or undefined, I can't remember which one, for the empty state. And for anything else, like it basically constructs a very small object where it's just like a value plus like one tag for the value and one tag for the next element of the list. So it's a very compact data structure. It has pretty good performance despite, like, I mean, linked lists are never going to perform as well as arrays for certain operations, but in general, they can be pretty performant. And for a lot of coding idioms, it's kind of more convenient to use a list. If you're writing pure code where you don't want to have to do a lot of copying, then lists often perform better. But if you want to do more like stateful operations where you have where you're going to be doing a lot of updates to a mutable structure, then arrays often make more sense. So it depends a lot on your application.
Yeah, no, that was a great answer, Alan. I think like you mentioned a great point, which is the fast appends to the beginning of the list. And I think it may be the end of the list too, but specifically for the middle, if you want to insert anything in the middle, it's O of n. So for the tokenizer, I probably could have used a list because I was doing so many appends to the end. But yeah, that's something that I could definitely consider and is a valid point too.
Yeah, sometimes you could do a hack where you build up a list in reverse so that you can get that constant time append to the beginning.
That is
and then
trick.
At the very end, you reverse it, which is a linear time operation. But like, if you're already finished, then it's like relatively cheap.
Right. Yeah, it's like O of n squared versus O of n. Yeah. Big O. We do too much big O at the University of Illinois. So
makes a difference, but
yeah,
can get you.
Yeah. Cool, everyone. I'm gonna turn off the recording because I think this is more free flowing. But actually, what do you think, Peter? Should I keep recording?
No, I don't think so. I think it's just a discussion.
Yeah.